where we left off. So we were on page 100, and I introduced to you guys these two special cases where it's actually easier to look at the opposite chance than the actual chance that they're asking for. So I want to do let's see, we'll do a couple more of these examples, and then we're going to kind of move on. But the biggest piece of advice that I can give you guys for probability is that when you read a question, because probability, I'm not going to lie, probability is hard. It's overwhelming, especially if there are multiple things going on in the question. So what I want you guys to do when you're doing these questions is don't think about doing everything at once. So like if I read, let's just do, this is an easy one, the first one. What's the chance of rolling a fair die twice and getting a 5 and then a 6? So don't think about rolling twice, think about rolling once. So the question's asking, what's the probability we get a 5 and a 6? Okay, so think about your first roll. Don't think about the whole thing. So on my first roll, the chance that I get a 5, we know is just 1/6, right? There's 1 5 and 6 sides to the die. Then they're saying, and we get a 6. So and means to multiply, so multiply 1/6 times, and then the chance of getting a 6 on the second roll is still going to be 1/6. So maybe that looked intimidating at first, but if you think roll by roll for dice or draw by draw for cards, it's going to make the problem a little simpler to understand. So let's see, I want to do 10B as well. I'm going to skip some of these. You guys can do them as practice if you want. These are really good practice problems, but we don't have time to do all of them today. 10B, this is another one I want to do. It says, what's the chance of drawing 3 cards without replacement and getting no hearts? So my question for you guys is, a lot of people will read this question and say, oh, that's one of my 2 special cases. Like, do I have to use this 1 minus stuff? And do you guys think, so this is a question, do you think no hearts and not all hearts are the same thing? No, good. Most of you guys said no. They're not the same thing, right? So I don't want to use the only time I have to use this 1 minus stuff is if the question's asking me about at least 1 or not all. This 10B isn't asking me about that. It just says, what's the chance of getting no hearts? And this is actually a pretty, it's not as complicated as it may seem. It's a straightforward probability. We can calculate it directly. So this means I want to know if I'm drawing 3 times, what's the probability I get not a heart and not a heart and not a heart, right? No hearts every single time for all 3 draws. I don't have to do the 1 minus. That would be for not all. Just kind of an example of how they're different. Like you can think about just in the English language when you use the word no and not all. Like if you tell your parents, maybe at the end of the semester, your parents are like, hey, what'd you get in your classes? If you're taking 5 classes and you tell them you got no A's, that means you got 0 A's, no A's. But if you say you didn't get all A's, well, maybe you got a few, maybe you got 0, maybe you got mostly A's, but not all is complicated. It encompasses a lot of different scenarios. No is just, there's none of them. So no heart and no heart and no heart. And we can do this directly. What's the chance on my first draw out of the deck that I don't get a heart? Well, there's 13 hearts in the deck. Oh, oops, I guess I already wrote that. Apparently, I already said that. Okay. Well, there's 13 hearts in the deck. And so the chance of getting a heart is 13 out of 52. The chance of not getting a heart would be everything but that, right? So there'd be, how many would that be? 39 non-hearts. So the chance of not getting a heart is just 39 out of 52 on my first draw. And if it was just 1 draw, that would be my answer. But they're asking for 3 specific cards. It says drawing 3 cards without replacement. So the chance that I don't get a heart on my second draw is actually, so it's not exactly the same because it's without replacement. Now I only have 51 cards left, and I took out one of the non-hearts. So I only have 38 non-hearts left. And then for the very last one, the third one, I only have 50 cards left, and I only have 37 non-hearts left. So I can leave my answer like that. So any question that doesn't have at least one or not all, you can just calculate directly like we just did. Okay, let's look at what I asked you guys originally. No and not all, are they the same? Let's see how not all is different. Let's see, where's my not all? Maybe this one, 13A. It says, what's the chance of drawing 3 cards from a deck with replacement and not getting all hearts? So the probability of not getting all hearts is complicated. That's definitely one of my 2 special cases. If I draw 3 times, not getting all hearts, well, that means I could get 0 hearts, right? That would be not all hearts. Or even if I get 1 heart, that would be not all hearts. If I got 2 hearts, that would still be not all hearts. The only thing that's not included in not all is all. So instead of calculating, I could calculate this directly. It's possible, but I'd have to find 3 separate probabilities, and I don't want to do that. I want to use my rule. So my rule up at the top says the probability of not getting all of something is just 1 minus the probability of getting all of it. So I'm going to write down the probability of not getting all hearts is just 1 minus the probability of getting all hearts. And these 2 things are exactly equal, so let's not focus on the complicated one. All hearts, we can think about that pretty easily, right? We said there were 13 hearts in the deck. So I'm drawing 3 cards, but again, let's think about the first card. The chance that I pull out a heart is just going to be all hearts, well, 13 out of 52. That's the chance of getting a heart. And I want that. I want to get all hearts because, again, let's not focus on the complicated not all. Let's look at the other side of the equation. So let's see. It's with replacement. So my chance of getting a heart on the second card is actually the same. I still have 13 hearts and 52 cards because I took out my heart, but I put it back in. And if it's with replacement, the deck doesn't change. So I could actually write this. If I wanted to, I could write this as 1 minus 13 over 52 cubed. Okay. So that's kind of the gist of these probability questions. So the only time, all of you guys on the test, when you see the test, the only time you're going to circle an answer that has 1 minus in it is if the question says at least 1 or not all. If not, you can go ahead and calculate the probability directly using the multiplication rule like we did for 10b. So these are the 2 special cases where it's easier to look at the opposite chance. All right, so just to make sure, so we did none, we did not all. Just to make sure you guys are totally good with this, we're going to do one more example with at least 1, because we haven't done at least 1 in a while. And actually, this example is, we're gonna come back to this conditional probability. This example is a little further along. It's on, let's see, I hope all of your books are the same pages. It's the birthday problem. It's birthdays in my book, in the Spring 2020 book. It's page 105. All right, so this is our first, I guess this isn't our first example, but this is going to be the first real life example. Cards and dice can sometimes get a little boring. So let's actually ask this question. It says, what's the chance that at least 2 people in this class share a birthday? Okay, so before we actually go through and look at how to do this, I want you guys to intuitively think, what do you think this probability is? So first of all, what we're going to do an eye clicker. We're going to start, our first eye clicker question is just to see how many people are here. So the question is, for the birthday problem, in honor of the birthday problem, how old are you? This is a great one. There's no wrong answer. All right, this is good. We'll probably have over 400 people here. Go ahead and vote. I'm going to stop it in a second. We got a lot of people here. Good. Okay, I'm going to stop. How old are you? And we are going to see, most of you guys are 18 and 19. That sounds about right. I used to tell the students how old I am, but I'm too scared now because I'm old. Okay. So we know there's about 400 people here, but that's not an interesting question. If I asked you guys this question, what's the chance that in a group of 100, or if I said in our class, what's the chance that there's at least one match of birthdays in our class? That wouldn't be very interesting because we have more than 365 people in our class. So even if the first 365 people had different birthdays, there's bound to be someone there's bound to be a match, basically. So we have a huge class. Let's think about 100 people. I want you guys to answer this intuitively. If I asked you, without doing any math, without giving you any preview of this question, what's the chance that in a group of 100 people, there's at least one match of birthdays? What would you say? So you're going to vote. What do you think is the answer to this question? Intuition, where do we stand? So think of, 100 people. So probably like everyone who's standing in front of me, this is like 100 people. So you guys, do you think there's a match between anyone sitting right here? So the question in the book, it says, what's the chance there's at least two people in this class that share a birthday? In other words, at least one match. Same thing. Is today anyone's birthday? Anyone today? What's today? March 5th. Is anyone's birthday today? Oh, someone's is Friday. No one's is today. Yours is today? Oh, happy birthday. Give him a round of applause. Wow, the birthday problem on your birthday. Happy birthday. But only one? There's only one? Nobody else? Okay. All right. So far we don't have a match. Okay. Let's see what you guys said. Okay. Most people said between 10 and 50%. So you guys think in 100 people, it's probably low that there's a match, right? Overall, we can say that's the consensus. So we're gonna look at how do we solve this problem we can use our rule for at least one, right? At least one match of birthdays. We can actually solve that mathematically. But first, I wanna do a demonstration in class. We might as well go ahead and test this out. So I'm going to ask some of you when your birthdays are, and we're going to keep track. We're going to see if we get a match. We'll see do I have to wait? Maybe we won't get a match. Maybe I'll have to ask like 100 people, and it'll take forever. We're going to see. So I have some assistants here to help with this. So Maya is one of our TAs. You guys may have seen her at office hours. We are going to, hold on. Oops, not that. We're going to actually document the birthdays. So she's going to click on the days as I ask the birthday. And this was an app that was developed by a computer science professor, Wade Fagan-Olmschneider, if you guys know him. He is also here sitting in on our Stat 100 class. Wade, thank you for making the birthday problem real. Okay, so we're going to start with you. I'm just going to ask, what's your birthday? January 11th. Birthday? October 24th. May 20th? October 23rd. Oh, we're close. We almost got a match. Okay, what about you? December 7th. September 21st. March 12th, coming up. December 24th, Christmas Eve. Am I going too fast? You good? Okay. Don't say it yet. September 10th. September 19th. September 2nd, wow. Hi, September. May 1st, August 12th, July 15th, April 27th. Hold on, even if there's a match, we're gonna see a group of 100 people. August 18th. Ooh, we're going a long time. November 25th. November 30th. August 2nd. Whoa! They're sitting right next to each other. This is insane. Do you guys know each other? Did you know you had the same birthday? What is the probability of that? I'm like, my mind is blown right now. Okay, well, that was weird. And that was quick. Maya, how many did we need? 20. So I had to ask 20 people, and we got a match. So if 20 people we got a match, is that a fluke? Is this probability really as low as what we originally thought? So how many of you guys, just out of curiosity, how many of your birthdays have already been said? Raise your hand. Ooh, yeah, we got a lot of matches. Whoa. Okay. All right. So let's figure this out. So thank you for your assistance. All right, we're gonna go back. So now let's actually figure this out. What is going on? So we're gonna say, let's see. I said there's 100 people. There's more in this room, but again, for the sake of demonstration, we're gonna say 100. And the question is, I'm gonna go ahead and write down the question. What's the probability that there's at least one match of birthdays? So the question is, did we get lucky? We had 20 people. I just went through 20 people and we got a match. We did get lucky because they were sitting right next to each other. I wonder if any of you guys, my birthday's October 10th. Does anybody match me? 10-10? Oh, nobody matches me? That's okay. Last semester I did the birthday problem on my birthday. It was epic. But in the spring I can't, so this is the next best thing. All right, so at least one. I just said, there's two cases where they're complicated, right? At least one match of birthdays. That would mean that you guys, let's see, if 100 people, at least one match, that would be one match or two matches or three matches or four matches or five matches. That would be a nightmare to figure out. The at least one is complicated. So instead, what I can do, so at least one match means there could be one match, there could be two matches, all the way up to 100 matches. Let's see, there we go, 100 matches. So I don't want to do that. That sounds horrible. Instead, I'm going to use our rule. So the rule is that the probability of getting at least one match is equal to, we can use the 1 minus the probability of getting no matches. Right? So at least one, the opposite chance is none. The only thing that's not covered in at least one match is 0 matches. So finding the probability of 0 matches is still a little intimidating with 100 people, but it's not as bad. So what I would do, actually, I'm gonna just get rid of that. I'm just gonna do this. We're just gonna do it without these prompting questions. So the chance, let's see, of getting no matches. So it says do it stepwise. Line the people up and figure out the chance of no matches for each person. So basically what I would do, my answer is going to be 1 minus, and then the chance that all 100 people don't match. So the very first person, if I'm the first person, I don't really matter. I could write this down if I wanted to, that there are 365 days that I could have as my birthday out of 365. In other words, there's a 100% chance that I don't match anyone because I'm the first person. So I don't even actually have to include me as the first person since we're looking at matches. So if she is the second person, what's the chance that she doesn't match me? So my birthday's October 10th. What's the chance that her birthday is not October 10th? 364. Yeah, most of you guys got it. 364. So I want me, person 1, so I'm going to call me n equals 1, person 1, to not, and the second person not match. So I'm going to times, right, for the multiplication rule. The chance that the second person doesn't match me is 364 over 365. Okay, so person 1, person 2. When's your birthday again? January 11th. So the third person, Brenda, the chance that she doesn't match us two is going to be, so she can't have January 11th, is that what you said? January 11th or October 10th. So the probability that her birthday isn't either of those 2 days is what? 363 out of 365, right? I'm also ignoring the leap years, so pretend it's not 2020. And then I'd have to do this for 100 people, right? You kind of see the idea that every time we add a person, the probability of the next person not matching gets smaller, right? So like the fourth person, I could add for the fourth person, the chance that they don't match the three of us, well, there's 362 remaining days out of 365. And I'd have to do this, 365, all the way up to n equals 100. So I would never make you guys do 100 probabilities on a test, but you could just technically put all of these into your calculator. I would definitely use a program to do this because I don't want to type that long. But when we do this, we're taking all these probabilities and multiplying them together. So essentially what we get is 1 minus, when I multiply all these probabilities, I actually end up getting basically, it's really, really close to 0, a really small number. So it's 1 minus about 0, and this ends up being 99.99%. Answer to the birthday problem goes against what we thought intuitively. Actually, in a group of 100 people, I would bet money that there's at least one match. Even when we did it in class, we only needed 20 people to get one match. So it's kind of like, intuitively, you were probably asking, does anyone have the same birthday as me? But if you think about, like, if you guys have Facebook, you probably have people with multiple birthdays on the same day. You probably know at least 2 people that share the same birthday. So this probability actually is huge. And if we think about our iClicker, I don't think hardly anyone said close to 100%. But that's actually the answer. So if you guys are like, maybe if you're at a party this weekend, you can pull out this fun fact and share statistics with the world. I sometimes do that and people don't like it though, so. But yeah, this is a classic problem that a lot of statisticians have studied. It's kind of weird, but you really only need about 20 to 25 people to almost guarantee that you'll get a match of birthdays. Maybe you could try it if you're at like a big party. I'll send you my app. Okay. So, yeah, that was that. This is important, right? The chance of no matches after 366 people is 0. Because if I asked, even if the first 365 people were all born on different days, there's only 365 days, so the next person would have to match. So I could have said at the beginning, there's a 100% chance there's at least one match in this room, because we had about 400, we had over 400 people. The last part of the birthday problem, I just want to definitely answer this question too. It says, here's a very different question, but it's kind of related. What's the chance that at least one person shares your birthday? So this isn't as high. This is, what's the probability that there's at least one match to me? So like if I was doing this, you can think about yourself, think about your own birthday. So I want to know, what's the chance there's at least one person that matches me? So again, I'd say, well, that's 1 minus the probability that no one matches me. So I don't care if they match each other, they just can't match me. So if I was going to go ahead and do this, let's see. The chance that no one matches me. So my birthday's October 10th. So we already said the chance that the first person doesn't match me is pretty high. 364 over 365. So that's for person 1. But the second person, I don't care if they match the first person, they just can't match me. They just can't have my birthday. So the chance that the second person's birthday is not October 10th is actually the same, right? Because I don't care. They could match the first person. That's totally fine, but they just can't match me. And then the third person, again, I don't care about any other birthdays except mine. They still have a 364 out of 365 chance of not matching me. every single person I ask, the probability they don't match me is 364 over 365. It's different if I think about matching other people, but just me, this is always the probability. So if I have, let's see, if we had 100 people, if I was one of the 100 people, I'd have to raise this to the 99th power, basically. This is a little easier to put in your calculator. And you get around 24%. So this might have been the question that you were thinking, well, what's the chance that someone has my birthday? Which is different than what's the chance that at least 2 people have the same birthday. It doesn't even have to be mine. It can be any birthday. So that's the birthday problem. That's at least one example, a really famous one. Maybe some of you guys have seen it before, but if not, it's kind of cool. Any questions? All right. So, like I said, you guys will get plenty of practice with the at least one and not all on the homework that's due next Tuesday. But so this class I was gonna do 3 things. First is the birthday problem. Second is this idea of conditional probability. So I'm back to page 101. All right, so the good thing about this next part, this is the part of probability that most students think is the easiest, so that's good. We're gonna look at conditional probability and tables. So the definition, what I mean by conditional probability is this. It says the conditional probability of an event B is the probability that the event will occur given that A already happened. So conditional probability right here is written as the probability of B given A. So the line, the pipe symbol means given in statistics. So this is red. So you guys might see some of this notation on the homework. All this means is what's the probability? Probability of B given A. So the line just means given. It's not anything fancy. So what's the chance that something happened given that something already happened? So there's usually 2 conditions. And we can go ahead. So there's a bunch of different ways to teach conditional probability. And actually, I was just right before this class. Today, you guys probably don't know this, but today's the faculty retreat. So all the faculty from U of I actually go to the union, and we talk about teaching. And Wade, the other professor that was here, and I just did a presentation about conditional probability and how there's a bunch of different ways that we can teach this to students. So I'm going to show you guys the way that I think is the easiest, and then we'll look at a couple other ways. Maybe you'll like those better. But I'm definitely a visual person, so I like looking at tables. It says if a situation involves 2 or more conditions, a table can be really helpful. And students usually like this too. So the first example, it says, suppose a box contains 30 aspirin and 70 Tylenols. Half the aspirin and 10% of the Tylenols are poisoned. Fill in the table below. Okay. So we want to ask questions like this, like, A, what's the chance of randomly drawing a pill and getting a poison? What's the chance of getting a poison aspirin? What's the chance if it's aspirin given that it's poison? So there's all these complicated questions that we could ask, but the table is really going to help. So let's fill out our table first, and then we'll see how that's going to help us with the question. So I'm going to use what I'm given. It says there's 30 aspirin. So aspirin, I'm going to go over to the total and write 30. So always fill in the total column first. Will be super helpful when doing this. Total column first. So you want to know how many pills there are, and then there are 70 Tylenols. So 100 total pills. Okay, that looks good. What else? They said half the aspirin are poison. So of these 30 aspirin, half of them, which would be 15, are poison, which means that implies half of them are not poison. And then what about the Tylenol? It says 10% of the Tylenols are poison. So there's 70 total Tylenols, and 10% of them are poison. So 10% of 70 is 7. Right? So I'm in the poison Tylenol. I'm trying to figure out how many of those are there. And it says 10% of the Tylenol are poison, so 7. And then we can, the table, it's nice, the rows sum and the columns sum. So if there's 7 poison Tylenol, then the rest of the 70 are not poison. So that leaves me with 63 not poison. And then I might as well fill in total poison is 15 aspirin and 7 Tylenol, so 22 total poison. And then that means there are 78 total not poison. So your chances, I guess, are pretty good of not getting a poison. 78 out of 100. But A says, what's the chance of drawing a pill and getting a poison? Okay, so what's the probability of getting a poison is all that means. That's how I'd write it in probability notation. And I don't actually care. I don't care if it's aspirin or Tylenol. I just want to know what's the probability it's poison, and there's 22 poison out of 100 pills. So this is just 22 out of 100, which is 22%. Okay, let's see. So far, so good. What's the chance of randomly drawing a pill from the box and getting a poisoned aspirin? So what's the probability I get a poison aspirin? Well, I'm drawing out of the whole box, so there's 100 total pills, and then we can just see how many successes are there. How many poison aspirin? And there's 15 of them. We calculated up here, right? Half the aspirin are poison, so there's a 15% chance of getting a poison aspirin. So see how, so the table is definitely helpful. A couple more questions. It says, if someone randomly draws an aspirin, so if they pick one of these 30 aspirin, there's a 50% chance that it's poison. We want to know, does this mean that if someone draws a poison, there's a 50% chance that it's aspirin? So this is the idea, this is a question about conditional probability, because there's a condition. We're saying, what's the probability, what's the chance that it's aspirin, given, the line means given, that it's poison. So I'm answering, here I'll highlight the question, what's the chance that it's aspirin given that it's poison? So anytime you have a condition, now we're not looking at all of the pills. We're saying given that it's one of the poison. So I can actually, I'm going to ignore the rest of my table. I know I got one of these 22 poison pills. So the given is always our denominator. There's 22 poison, right? So we want to know what's the chance that it's aspirin given that it's one of the poison. So we know it's one of the 22 poison, and then 15 of those are aspirin. And then, let's see. If I wanted to change this to a probability, it's definitely not 50%. 15 out of 22 is 68%. We can multiply it by 100 to get it in percent form, and this is about 68%. Okay, so my table definitely helped me with that. Part D says, in all contingency tables, the numbers in the margins are called marginal probabilities. So the marginal probabilities are numbers like, there are 30 aspirin, oops, oh no. Well, maybe I shouldn't do that. I'm going to do it anyway. There are 30 aspirin. Kind of messed it up. But 30 aspirin, 70 Tylenol, 22 poison, 78 not poison. So those are the marginal probabilities. The other probabilities, the ones in the middle, like these, hopefully this doesn't mess it up. There we go. Those are called joint probabilities, because this is like, there are 15 poison and aspirin. There's 63 not poison and Tylenol. So it says the numbers inside the cells are called joint probabilities. Bless you. Okay. So, what does this want? Which answer is a marginal? Which one's a joint? So we can just look. This one I'm looking at 22. That is definitely one of the marginal ones. This one I'm looking at 15. That's one of the joint. So I can say my answer to A is marginal. My answer to B is joint. And then B is joint because part B says, what's the chance of getting a poison aspirin? So we're looking at two probabilities, or two conditions. We're looking at it being poison and aspirin. All right, so I think that's good for that example. This last part just says, hey, just to let you guys know, the probability of A given B isn't always equal to the probability of B given A. So sometimes they're equal, but sometimes they're not. So it doesn't have to, those don't always have to be equal. And we saw that in part C. So let's see. I'm going to do a couple more examples of this, and then we'll do our last thing. So next page. Okay, page 102. So this example, if you guys pay attention to any example today, it should be this one because it's basically on the homework. This is number 2. It says, suppose jurors, so, court system, jurors, jury selection, the jurors make the right decisions 95% of the time. And 80% of all defendants are truly guilty. So let's fill out our table for, let's just say we have 1,000 people. I'll always tell you guys how many people to fill out your table for, but really it doesn't actually matter. Regardless of how many people you have, your probabilities are going to be the same. So let's do 1,000 people. So I want to fill in my total column first. So I need to know what piece of information tells me either what percent of people are innocent or what percent of people are guilty. And if I look at this, let's see, right decisions, it's telling me about the right decisions, but what I really need is this. It says 80% of all defendants are guilty. So of these 1,000 people total, 80%, I'm going to fill in this guilty column first. 80% of 1,000 is just 800. So 800 of them are guilty, which means 200 of them are innocent. So always fill out your total column first. You'll know how many people there are total. I just gave you guys the 1,000. We could have done 100 if we wanted to. We could do 500. We could do whatever. And then now we can fill out the rest. So it says the only other piece of information I'm given is that suppose jurors make the right decisions 95% of the time. So for innocent people, so for the 200 innocent people, is the right decision for the innocent, should they be acquitted or convicted? Acquitted, yeah, most people said acquitted. The right decision, so the right decisions, I'll put a double star. The right decision for innocent people, they should be set free, right? They should be acquitted. The right decision for guilty people is that they should be convicted if they're guilty, right? So make sure to know that for the homework, that the right decisions, the innocent people should be correctly acquitted, and then the guilty people, those people should be convicted. Right? We want to minimize the amount of innocent people getting put in jail and the amount of guilty people getting set free. Okay, so this happens, the right decisions happen 95% of the time. So for these 200 people, 95% of them will correctly be acquitted. Right? So of the 200 innocent people, 95%, which is, if we do this in our calculator, this is 190, which means only 10 of the 200 people that are innocent will be convicted. You can think about which one of these is worse. I don't know. And then the right decision for these 800 guilty people, they should be convicted. So they'll do that 95% of the time. So 95% of 800 will correctly be convicted if they're guilty. So this gives me 760. And then how many are left? 40, right? 40 of the guilty people will be acquitted, will be set free. So let's see, 190 plus 40 is 230, and then 10 plus 760 is 770. So I made my table before I even looked at the questions because I know the table is going to help me answer the question. What's the chance that a person is convicted given that they are innocent? So we want to know what's the probability that they're convicted. Ooh, that's not good. Convicted given that they are innocent. So we don't want, hopefully that's low. So we're given that they're one of the innocent people. So I'm going to look at just the top row, right? There's 200 innocent people. I'm given that they are innocent, so there's 200 total innocent people. What's the chance that they're convicted? Well, 10 of the 200 people are convicted. So we're saying, given that they're innocent, what's the chance they're convicted? So they're one of these 200 innocent people. Only 10 of those 200 people are going to be convicted. So if I didn't have the table, this would be hard. This would be hard to find, right? I like the table. It helps. Same with part B. What's the chance that a person is innocent given that they are convicted? So this kind of sounds the same, but it's actually the opposite. What's the chance they're innocent given that they are convicted? We said these are not always going to be equal. So probability that they're innocent. Now we're saying given that they're convicted. So I'm not looking at the acquitted people. I'm not looking at the total. If I didn't have to hold this mic, I would get rid of the first and third columns, but we're just looking at the convicted column. We're saying given they're convicted, they're one of the 770 people who are convicted. What's the chance that they're actually innocent? Well, of these 770, only 10, again, are innocent. So this probability is super small. 10 over 770, we can figure out what that is with our calculator, and it's going to be something really small. So 10 over 770 is actually, it's about 1%. So it's tiny, which is good. All right. Any questions on conditional probability? All right, so you guys, I would recommend making a table. On the test, spoiler alert, I'll give you a table if you want one. Or I will give you one even if you don't want one. So it'll be there to help. But the last example I want to do for this is actually another famous example. This is about medical tests. So a lot of the examples we use are about certain types of tests that aren't always 100% accurate. So medical tests aren't always 100% accurate. Right? Because you can get a false positive or a false negative with most medical tests. I don't actually know of any that are 100% accurate. So this is an example I kind of want to do, so we've done the tables. I kind of want to show you how we could do this intuitively as well. This is an example about screening donated blood for AIDS. So the test is called ELISA. You can read about it if you want. But basically, anytime anybody donates blood, it goes through this system and tests if the blood sample has AIDS or not. So the question that I want to ask, okay, here it is. It says, if the blood sample has the AIDS virus, this is a good test. There's a 99% chance that ELISA will correctly give a positive result, which is good, because if the blood is contaminated, we don't want to use it. So there's a 99% chance the test will correctly mark the positives. But if the blood sample doesn't have AIDS, unfortunately, there's still a 6% chance that ELISA will incorrectly give a positive result. So there's a 99% chance it will correctly give a positive result. There's a 6% chance, though, that even people that don't have AIDS, they'll get this positive result just as a mistake. And then about 1% of the blood samples are truly contaminated. Okay, so 1% of people, they're saying 1% of people who donate blood have AIDS. Test is 99% accurate, but has a 6% chance of getting a false positive. So I want to do this, again, kind of an intuitive example with 100 people. So we want to know, I want to look specifically at question B. I want to know what's the chance that someone has AIDS given that they got a positive test result. Okay, so we'll do the same thing we did with the birthday problem. How about you guys vote? Like, maybe we should say, okay, we said 100 people. There's 100 people standing right in front of me. And I'll take one for the team. Let's pretend that I got a positive test result for this test. Pretend I got a positive result. And should I be concerned, is the question. What's the chance I actually have AIDS? I don't, but for this example, I do. What's the chance I actually have AIDS if I got a positive result? I didn't want to ask for a volunteer for that one. So let's pretend it's me. What is this probability? Should I be concerned is my question. So before we do the math, let's again test out our intuition. What do you guys think? I have all these questions. Where's the one I want? Here we go. Okay, so go ahead. Don't do any work. Just intuitively, like knowing about the test. Should I be worried? All right, go ahead and vote. Your intuition, your first guess, what would you say? I'm going to stop. But there's more people. Okay, I'm going to stop for real. Stopping now. Okay, most of you guys, so some people said less than 25%, but most people said between 75 and 100%. So most of you guys are like, all right, this test seems pretty legit. I should be very concerned. I should be concerned. Okay, well, let's test. Let's see. So we said we're going to look at 100 people. So let's write down what we know. We know there's 100 people, and the question said that 1% of people actually have AIDS. So 1% of 100 is easy to work with, right? 1% of 100 is just 1. So that means 1 person has AIDS, and then 99 people do not. People do not. Okay. So the 1 person, we're saying, that was me. And the test, let's see, what else did it say? It said 1% of the blood samples are truly contaminated. It said the test was 99% accurate. So if I'm the person that actually has AIDS, I'm going to assume that I got a positive result. 1 positive result. Right? 99% accurate. I probably got a positive result, more likely than not. 99%, close to 100. So I'm going to say, me as the 1 person, I probably got a positive result. But the test, we said, is far from perfect. We said 6% of people without AIDS don't actually have AIDS, but they get a positive result. So 6% of 99, let's just estimate, 99 is close to 100, 6%, about 6 people. 6 of these people who don't have AIDS will get a positive result. So I'll have 6 positive results that we're going to call a false positive. 6 positive results. These are false positives. So these aren't good. Okay. And maybe I honestly contemplated changing this example because of all the coronavirus stuff. I didn't want to scare anyone talking about these medical tests, but I did it anyway. So the answer to the question, though, what is the actual answer? What's the chance that someone has AIDS given they got a positive result? Well, given that they got a positive result, there were 7 people that got a positive result, right? the person that has AIDS would get it. But then 6 people that didn't have AIDS would also get a positive result. So I would have 7 total positive results, but only one of them, only me, was the one that actually had AIDS. So with this test, what happened was, because only 1% of people had AIDS, there ended up being more false positives than true positives. Yes, that one person will most likely get a positive result. But there's so many more people who don't have AIDS, and there's a 6% chance rate of false positives. So my answer, 1 out of 7, if I simplify that, it's about 14%. It's not high. So again, see, probability is fun, right? No. But that shows that our intuition was just a little bit off, and we can always double check by either building a table. I could have done this example with a table. You can kind of just write down what you know. You can always do an example with 100 people and think about what it means, what the given information means. Or the last way, let's see, I'm going to skip this next example. I feel like we got it. Page 103, skip. The last way that we could do these questions is with something called Bayes' rule. Bayes, B-A-Y-E-S. And Bayes' rule is really a formula. How many people, do you guys like formulas? Is anyone here who loves formulas? Some people love them, okay, that's good. I like them. I was a math major, they're fine. So you can actually do all of the conditional probability questions using Bayes' rule. And so here's the formula for Bayes' rule. It's conditional probability. The probability of A given B is just equal to, and then there's that formula. So I will never force you guys to use Bayes' rule, but it is, if you like formulas, this is a surefire way for you to get the probability. That definitely works. But for the sake of time, we're not going to go over an example using Bayes' rule just because, again, you can always do it with the tables, and if you like formulas, here it is. Here's the formula.